Hello, everyone. My name is Travis Addair, and thanks for coming to this presentation. I'm from the Michelangelo team at Uber. That's our machine learning platform team. I'm here to tell you about the recent work that we've done in collaboration with the Anyscale folks to bring Horovod support to Ray. So Horovod is a distributed deep learning framework for TensorFlow, PyTorch, and MXNet. It allows you to scale up your training of your deep neural networks from one machine, one GPU, up to any number of machines, any number of GPUs, which as folks who are at a Ray conference, that should sound like something that's a very familiar concept to them. But the nice thing about it is that it has a very simple to use and flexible API that works very natively with your existing TensorFlow, PyTorch, and MXNet training scripts. And then once you add just a few lines of code, you can get running with potentially any number of GPUs to train up your models. So let's get into things by quickly going through a refresher on the deep learning training process. So when we do deep learning, we typically have some labeled data, so this would be supervised learning coming in. The data is fed through the network. It creates an output prediction, and then it's compared against the label. And based on that, we have an update step, backpropagation, where we use the error to adjust the weights of the model. But the first thing you'll notice here in this diagram is that these gradient updates here, the layers are sequential, so it's not a super parallel problem natively. This isn't something like a typical Spark application, for example, where we can just kind of divide up the work kind of however we want, and then at the end we aggregate everything back together and call it a day. We have to be a little bit more careful about how we think about distributing this workload. And so in the distributed deep learning setting, we typically have two approaches that are taken in order to scale up the training process. The first is what you call model parallelism. This is where you have the different layers of your network distributed across different devices. And the second is data parallelism, where you have the same model in every one of the GPUs, for example, but they're each processing a separate piece of the data. So a separate portion of the mini batch. Now, model parallelism is very useful when you have a very, very large model. So a model that where all the parameters in it might not even fit on a single GPU. That's a typical scenario where you need model parallelism. Data parallelism, however, is what most people typically encounter when they are trying to scale up their training process, because they have a data set that is so large that completing a single epoch on a single GPU can take a very long time, say maybe hours, something like that. The total training time in some cases for very large data sets can creep up into days or even weeks to train. And so when you are able to shard the data set to speed up training, as long as your model can tolerate a larger batch size, what you find is that you can get the training time down to hours or even minutes in some cases for these otherwise extremely time-consuming training processes. So Horovod is the framework that we developed here at Uber to address this data parallelism problem. It has since been open sourced. It's part of the Linux Foundation, and we welcome you to try it out and become a contributor if you find some way that you'd like to contribute back. As I mentioned, it's framework agnostic, so we support TensorFlow, Keras, PyTorch, MXNet. We have a generic backend that kind of works across all these different frameworks, so it's very easy to plug in new frameworks. And we support many high-performance features, NVIDIA's Nickel framework for kind of fast aggregation of these tensor gradients across GPUs, GPU Direct for RDMA across GPU devices, as well as RDMA in host memory if you're using MPI. And also we use a technique called tensor fusion that allows you to take small gradient updates and batch them together, which significantly improves performance. And as I mentioned, it's very easy to install, just 5 lines of Python and you're ready to go, or easy to use, I should say. And then easy to install as well, just use pip. Pip install Horovod. We have some environment variables you can optionally set as well. And the underlying concept behind Horovod is this technique called Allreduce. So Allreduce is a concept from the high-performance computing space originally, where you take your buffer that you want to sum. In this case, these are the gradients that we want to average across devices. And you essentially break it up into different pieces and message pass around the different pieces at a time in sort of this typically ring-based fashion, though in some topologies this might be a tree structure. And the result is that in the end you get the fully aggregated gradients, but it is done in a way that is optimizing to minimize the bandwidth of the operation. So in distributed training settings, normally you end up being bandwidth constrained, which means that, that's kind of the limiting factor that's slowing down your training process. And so by using this approach, what we find is that we can do this very efficiently and kind of eliminate that bottleneck, or at least mitigate it. And in practice, what we find is that Horovod scales really well. In many cases, what we find is that we get nearly 90% scaling efficiency, so very close to one-to-one scaling efficiency, even at very high numbers of GPUs. And in fact, this has even been pushed to some very extreme limits at Oak Ridge National Laboratory, for instance. They ran on IBM Summit, the world's largest supercomputer, with over 27,000 V100 GPUs, or Volta at least GPUs. And they achieved or sustained that upwards of 90% scaling efficiency, and ended up winning the Gordon Bell Prize for their work, Exascale Deep Learning for Climate Analytics. So Horovod's been a successful framework in the industry. It's used by many companies. We have many contributors from across the industry that help out with the project. And what we've found since releasing Horovod is a number of more recent trends at Uber that have kind of shaped our thinking towards how we do distributed training and how this integrates into the larger picture of deep learning workflows. So the state of the world today is that we have these heterogeneous compute setups where we end up doing, say, the ETL extract train load of the data using one framework, and then feature engineering using some different framework, hyperparameter search, distributed training, online serving. All of these end up using very different infrastructure, having different teams that maintain the SLAs and the services, et cetera. And ultimately, a lot of the engineering effort gets spent provisioning and stitching all of these systems together. So for example, we use Spark for doing the data loading and feature engineering. Then maybe we have a internal framework that we've talked about called AutoTune that does the hyperparameter search. And we use Horovod for distributed training, which has a separate infrastructure layer for provisioning the jobs and then connecting the Spark and the Horovod components together. And what you find is that this all becomes very complicated to maintain. So distributed training in particular, even outside of Uber, while Horovod is very easy to run, it has a very clean API. Provisioning the jobs, so doing the gang scheduling, setting up the containers, setting up MPI, is where most users run into trouble. And similarly, fault tolerance and auto-scaling, we've recently introduced an Elastic Horovod API, but finding a way to set up your workers to take advantage of it is something that is still a challenge depending on what kind of infrastructure you're working with. Hyperparameter search, there have been a lot of recent developments in this space. Explore-exploit approaches are becoming very common, so early stopping, giving sort of resource or time-constrained budgets for each of the trials. And so we're seeing a lot of interest in moving towards a dynamic resource allocation where we combine these sort of explore-exploit model with distributed training. So being able to kind of fan out during the explore phase and then scale up your more successful trials using distributed training in the exploit phase, as well as end-to-end workflows. So how do you move the data between stages? How do you take advantage of data locality, avoid having to materialize data sets by writing to disk? How do you provide random access into your data sets for the training process? And how do you make sure that you write this in a way that minimizes training serving skews? So you want to have a unified API that you can run in batch, as well as in streaming, as well as online serving. All of these things are complications that come up when you're dealing with writing these sorts of bespoke distributed systems. So this is where Ray comes into the picture. So Ray is, we like it at Uber, and the Horovod team has been very interested in it, particularly because it's an open platform, it's open source, it runs anywhere, Kubernetes, cloud, AWS, GCP, anywhere you want to run, Ray has already done the legwork to run there. It provides a general set of distributed compute primitives, so you get fault tolerance and auto-scaling out of the box, dynamic task graphs, actors to manage state, shared memory across different nodes, different actors. And it provides out-of-the-box ML infra as well. So RayTune, very popular hyperparameter search framework, comes with Ray natively. RLlib, most popular reinforcement learning library. So lots of good support in the ecosystem. So how can Ray help us out with the problems that I mentioned before? So distributed training, we're looking at Horovod plus Ray integration. So this is something that I'll be focusing most of the talk on today. Hyperparameter search, so we're in the process of adding Horovod plus RayTune support. And end-to-end workflow, so this is more forward-looking, but Horovod plus RayTune plus the recent work on Dask on Ray is something that has us very excited. So to kick things off, let's talk about Horovod on Ray and how to get started with it. So Ray support comes with Horovod in our release version 0.20 that came out at the beginning of September. And to start using Ray, you just need to install with Glue. So it only supports our Glue, not our MPI controller at the moment. And you install using this extra Ray, and you get the Ray dependencies thrown in there as well. And the key API that we expose with Horovod on Ray is this Ray Executor API. So it makes it very simple to get up and running. You just initialize your Ray cluster or attach to it as you normally would. And when you start this Ray Executor, you give it some Horovod settings, which, network interfaces, things like that, whatever you want to customize. And you just specify how many hosts and how many processes you're going to run on each of these hosts and whether or not you're using GPU. And then you launch this executor, and now you have the ability to start running Horovod jobs without having to do anything else. So all of the gang scheduling is all taken care of. Once this blocking call returns, you now have effectively a setup cluster environment where you can run Horovod jobs. So let's show an example of that. Here's a basic hello world. You have a training function that initializes Horovod, prints out the Horovod rank, and then returns that rank. So we're going to execute this, which will run it on all the workers, and then return a list of results. And that list of results will just simply contain exactly the number of processes that we allocated for the executor. And then when you're done with it, you can run multiple things, or you can just shut down when you're ready. Now let's show a little bit more of a practical example of this using the Stateless API that I showed. So one of the features we added to Horovod not long back is PyTorch Lightning integration, really great framework to abstract away a lot of the infra components of deep learning from you. And so here we have a training function that creates some data set, creates our data loaders, creates the model, and then what we call a trainer in PyTorch Lightning terms. And we specify that we're using the Horovod backend and we're using GPUs. And then we just call fit, and then the model will be trained and we return the model. And using our Ray Executor, we just pass in this very training function, and then we can pass in any arguments we want. So in this case, what our split between training and validation is going to look like. And then the first result here is going to be one of the models. So every one of the replicas will return its own model. And since we're using Horovod, all the models have the same state at the end of training. So we just pick the first one. And now we have a trained model locally that we can do whatever we want with. And we just trained it on maybe hundreds of GPUs. And then we shut down and we're good. But Ray has even more interesting features than just this. It also has the stateful capability, which is very exciting. So instead of running the whole training in one go and then returning the result, you can take advantage of Ray's statefulness by, say, defining some model that has a function that does a single training step. And then after you initialize your Ray executor, you maybe call this training step in a loop so that every call here is one step. And here you see the stateful execute API, where every worker is going to execute a specific function. So here we're saying worker.train. And then at the end, when we're happy with how many training iterations we've done, we can just call get weights to obtain the final result. And the thing here that's worth noticing is that this training step here, we didn't return any weights or any state or anything like this. All of the state is being handled by the in-memory caching layer of Ray, so that when we call worker.train, the updates are applied on the back end, and then we get the weights at the very end to return our result. And all of this was made possible by just passing in this executable class equals my model thing right here, which allows us to execute this API on all of the workers in parallel. And Ray also makes it very easy to run on top of AWS or in the cloud in general. So here's a very simple example showing how you would set up a distributed training job on AWS. So you assign a head node, give it some image, some instance type, and then all of your worker nodes will have this instance, this image type, and then install Horovod in there. And then you can start the cluster, wait for all the workers to start, and then submit your training script, and you're good to go. You're running on the cloud with Ray and Horovod. Now, another interesting feature that has been recently added to Ray is, to RayTune, is Horovod for hyperparameter search integration. So here's an example showing this API, now with a different color, so you know that we're looking at a slightly different use case here, looking at hyperparameter search in RayTune. So you have a training function that takes a configuration where your config defines what your learning rate is in this example. And here we're going to construct a model. We're going to use the Horovod API. So we have this distributed optimizer here that wraps our optimizer. Here you see the learning rate from our config. And then we do our normal training process, report the loss at the end of each step. And then this distributed trainable creator here will define how our Horovod job is going to be instantiated. So, whether you're using GPU, how many hosts, how many slots, it should look very familiar to the Ray executor that you saw before. And then finally, at the end, you just call get best config to get the best config. And so now you've effectively scaled up your hyperparameter search process to run on multiple hosts at once using Horovod. So what's next? So the next steps are pretty exciting. So Elastic Horovod is one of the big flagship features of the 0.20 release. And we're really excited to see this coming to Ray as a very easy way to get fault-tolerant auto-scaling distributed training in any framework. And then, like I mentioned, the Elastic Hyperparameter search as well. And at the end, I'll tell you a little bit about some of the things we're thinking about in terms of deep learning workflows on Ray. So Elastic Horovod, to give you a little context here, in the Elastic Horovod setting, we have a driver that has awareness of different hosts. And then some hosts may fail, and then some hosts may come online at a different time. And when this happens, we can context switch by removing the offending hosts, adding in the new hosts. And meanwhile, this host here that was otherwise fine is able to proceed in the training process with minimal interruption. So no need to tear down the whole process. No need to evict all the state from memory, etc. You can just keep going. And how does this work? So the driver will start, and then each of the workers will kick off, and they synchronize with each other, their state. And then the training process happens, and at some point a failure occurs. So the surviving worker will send a reset request back to the server saying, hey, I need to know who the new workers are. And then the driver will get all the other workers up and running, make sure that they all are aware of each other. And then these workers will once again synchronize state. Training will occur. The state will be committed. So in case a failure occurs in the middle of an update process, they can very easily roll back to the last known good state. So no kind of like intermediate state issue. And then this continues until a new worker is added or a worker is removed, etc. Now, taking this a step further, this idea of can we combine hyperparameter search with distributed training in an elastic context. So maybe the workers initially have one GPU each, and then we identify certain workers certain trials, certain sets of parameters that are doing very well. And we want to give more GPUs to them because we want them to train faster so that we can verify that they're good and just get the best model we can from them and then move on with our lives, right? So this is something that you'd call a typical like time constraint hyperparameter search problem. So you're bounded by wanting to complete either as quickly as possible or within some time limit. And there was some work done at Berkeley on this, this Hypersched algorithm that's briefly shown here, illustrated here. And that's exactly the kind of problem that they're seeking to address. And we want to, in the very near future, bring this sort of capability to Ray with Elastic Horovod. And this is some of the work that we have in progress. So stay tuned for that. Now, lastly, I want to briefly mention some of the thinking that we have around end-to-end deep learning. So Ludwig, for those of you who don't know, is an open source project originally developed at Uber that brings code-free deep learning to data scientists. So models can be defined in YAML. You can very easily iterate on local data sets on a laptop or scale up, which is what we're looking at now. And a variety of model architectures are supported, kind of state-of-the-art out of the box. You don't have to do any custom configuration in order to take advantage of that. And so some of the things that we're looking at for Horovod or for Ludwig is how do we scale this process up? How do we take it from being an easy-to-use toolkit to a true AutoML solution in the open source? And so for that, we want to go from doing this kind of a bespoke workflow of pandas, custom hyperparameter search, and then we use Horovod for distributed training. And we want to move this to something more scalable. So what do we do? So we have two options that we've considered, for example. Option A, we go with a heterogeneous model that I mentioned before. So we use Apache Spark for pre-processing. Then we write our results to, say, a Parquet file, HDFS, S3. And then we do our training with our custom hyperparameter optimization or Horovod, where the workers stream the Parquet shards from the distributed file system. But option B, how about we just use Ray? So we could have Dask running on top of Ray for pre-processing, RayTune plus Horovod on Ray for auto scaling and training plus hyperparameter optimization. And then in the glorious future, we could even have the Dask workers that pre-process the data coordinate using locality, shared memory, etc., with the training workers for random reads without having to do any kind of serialization or materialization of the data set to disk, and dramatically speed up the process of going from feature processing to training. And so naturally, the unified Ray backend sounds very appealing, and that's the direction that we're now exploring. So this is something that's planned for the 0.40 release of Ludwig, the next upcoming release. And the benefits that we've identified why we want to go this route. So no need to maintain, provision separate infrastructure. So you want to run this in the cloud, for example. You don't need to set up a Spark cluster and then a Horovod job and then set up like some kind of hyperparameter search using like multiple workers. No need to materialize the preprocessed data to disk, so you can leverage potentially data locality, co-location of the workers, or the actors in this case, to take advantage of shared memory. So your feature processing, all that data can be shared with the training workers without having to write anything. So to recap, Horovod is an easy-to-use, flexible framework to scale your deep learning training. But before the Ray integration, provisioning Horovod jobs was often a pain for some users who were not familiar or didn't already have a high-performance computing cluster to use. Now Ray makes it easy to configure a Horovod job on demand anywhere. And with Horovod plus RayTune support, we now have the capability to run Horovod distributed training in your hyperparameter search jobs on top of Ray. And coming soon, we have Elastic Horovod plus Ray for fault-tolerant auto-scaling deep learning training. And in the glorious future, Elastic Horovod plus Hypersched to scale up for the best performing trials. And if you're interested in finding a good auto ML solution that provides end-to-end training, take a look at Ludwig. With the support of Ray, we're going to be able to unify the infrastructure across all stages of the deep learning workflow and really scale this up into being a solution that runs efficiently in any environment. So thank you for your time, and special thanks to Richard from Anyscale for all his contributions to the Horovod project to bring this capability to Ray, as well as his work on RayTune to bring Horovod into RayTune. And if you would like to know more, please check us out on GitHub. Please feel free to reach out to me at Addair there. Feel free to take a look at the Ray docs as well to learn more. And also check out Ludwig on GitHub for more information about that project. So that's it. Thank you very much for my talk, and let me know if you have any questions.